Let we see about the uncertainty principle. We all have studied the definition for uncertainty principle, but how it is arrived, let we see in this section. So we are considering here an observable A in quantum mechanics and A expectation value. So here A minus expectation value of A we are defining as a deviation or uncertainty in the value of quantum mechanics, or we can say that a fluctuation in observable A. So usually we will be measuring the mean square deviation of the value, which is given as del A the whole square, which is a mean square deviation, and the formula for mean square deviation is square A square, expectation value of A square minus square of the expectation value of A. We already seen this in statistical mechanics. So there exists a state for which the mean square deviation of the observable A may be 0. So there is a state for which there is no deviation in the measured value of A. So here let me see for two variables A and B. What happens for two variable A and B, whether there exists a state for which the deviation of A and both deviation of A and B is 0. For that we are considering an operator A minus del minus I lambda B, where here A is defined as A minus expectation value of A. A minus I lambda B, A is for observable A and B is for observable B, and lambda is a real parameter. So we are going to here the A minus I lambda B is a adjoint operator. So the property we are using, the property of adjoint operator, positivity property, that is product of A into A dagger, expectation value of product of A into A dagger is always greater than 0. Here A is considered as A minus I lambda B and A dagger is A plus I lambda B. The product of these two quantities will be always greater than 0. Let me expand this to product A minus I lambda B and A plus I lambda B, and we get the equation A square plus lambda square B square minus lambda C. C is the commutation of bracket A comma B. Let me see how we have got this relation. So you can see here A minus I lambda B, A plus I lambda B. We are expanding it, A square minus I lambda BA plus I lambda AB plus lambda square B square. Here AB, BA, since it does not commute, we are writing as a separate AB minus BA and commutation bracket AB, and here I into expectation value of AB commutation written as C. So this is the expression what we have shown there. And here, so this expression is always greater than or equal to 0. That is, the minimum value of the expression is the 0. To find the minimum value, we are differentiating the expression with respect to lambda, and we are getting the lambda value as expectation value C by 2 B square. Let me see how we are getting this. So we are going to differentiate the expression A square plus lambda square B square minus I lambda AB with respect to lambda. So since we are having a lambda square, we are getting 2 lambda B square minus here lambda is here, so C. So finally we are getting the value for lambda. So substituting the value of lambda in the above expression, substituting the value for lambda in above expression, so you can see here lambda square is here. Lambda, for lambda square we are substituting C square by 4B square, and minus lambda C we are substituting for lambda into C. So both the second term and third term we are having the same term. 1 by 4 minus 1 by 2, we get minus 1 by 4. So the above expression is greater than or equal to 0. So this is the final expression. Expectation value of a square, expectation value of b square greater than expectation value of c square by 4. So you can see here, substituting the value of c as the commutation bracket of a comma b, and a is written as del a, that is the deviation of a. Already I have seen. So this is the general statement of uncertainty principle for any observable a comma b. That is the deviation of a, deviation of b is always greater than or equal to 1 by 4, commutation bracket of a minus a comma b. So if you are taking a and b to be a canonically conjugate pair of operators, we get commutation bracket of a comma b is equal to I h cross. Therefore we get del a into del b is always greater than half h cross, because substituting the value of a comma b as I h cross. So if we are substituting for instead of a x and instead of b p, that is the position and momentum, del x into del p always greater than h cross by 2. This is the general statement. This is a particular statement for canonic conjugate variable x and p. Therefore we could not measure the precise value of position and momentum simultaneously. So the deviation of the product of deviation of x and p is always greater than or equal to h cross by 2. This is the uncertainty principle.